This is Geometry, Unit 7, Day 2. We're going to apply the Pythagorean Theorem. When we look to the Pythagorean Theorem only works if you have a right triangle. And if you have a right triangle, and if you have two sides that are known, and you're looking for the third side, then the square of the lengths of the hypotenuse is equal to the sum of the squares of the lengths of the legs. When you have a right triangle, across from the right angle is considered your hypotenuse. The other two sides of the box are considered your legs of your right triangle. So another way to write out the Pythagorean theorem is to write it as hypotenuse squared equals leg squared plus leg squared. I suggest to write the hypotenuse part first rather than, for example, a squared plus b squared equals c squared, because later on in lessons when we're talking about some inequalities, it'll help to have the hypotenuse first. It'll make it flow a lot better. So we'll come down to example 1, and here it looks like we're trying to find the length of one side of a right triangle. We know two sides already. It's a right triangle, so we can use Pythagorean theorem. Across from the 90 degrees is your hypotenuse, so your other two sides are called the legs of the triangle. So using the concept of Pythagorean theorem, hypotenuse squared equals leg squared plus leg squared. X is your unknown. Now do notice that the unknown does not always go alone on the side of the equal sign. Sometimes the unknown will be added to another square and you have to solve for it by subtracting. You need to put them in the order of hypotenuse squared equals leg squared plus leg squared. It doesn't matter which leg goes in that spot. We get 49 and we get 576. So when you add the 49 to the 576, we get 625. Then we take the square root of both sides, and that comes out to be 25. So x is 25. Notice how we started out with positive integers, and when we solve for the missing side, we also got a positive integer. That's a special type of Pythagorean theorem triangle. That's called the Pythagorean Triple, because they're all integers, positive number integers for geometry. And we'll talk about that later on in the lessons. In this case, a 6-foot board rests underneath a doorknob, and the base of the board is 5 feet away from the bottom of the door. Approximately how high above the ground is the doorknob? So I'll redraw the triangle so we can see it a little better. So we have a right angle because the door stands up at 90 degrees. The board is 6 feet long. The board lands on the floor 5 feet from the door, and the door where the knob is located is x feet tall. Because the 6 is across from the 90, that's considered the hypotenuse. The 5 makes part of the box, the x makes part of the box, so we know those are considered the legs. So we're going to have hypotenuse squared equals leg squared plus leg squared. In this case, the 6 is the hypotenuse. We know that value. We don't know one of the legs, so that's where your variable is going to go. The other leg is 5. It doesn't matter what order you put the x and the 5. They just both, in this case, they're both legs. They need to both be on the same side of the equal sign. 36 and 25. So we'll subtract the 25 to the other side. So we get 11. And to get rid of the square on the x, we have to take the square root. So x is going to be the square root of 11. What is approximately the square root of 11? We know that 3 times 3 is a value of 9. I know that 4 times 4 is a value of 16. So 11 sits in between 11 and 16. So you know the decimal version of square root of 11 is between 3 and 4. And that makes sense with our right triangle. The hypotenuse has to be the longest side. We know the leg has to be shorter than that. 3 and 4, between 3 and 4, is clearly shorter than the 6. It happens to be the shortest side of all the triangle. Now we're going to find the area of an isosceles triangle. So we'll start out with the triangle. We know 2 of the sides are 17. The other side is 16. So to answer the question of what's the area, to calculate area, we need to know that half of the base times the height is how you calculate area. My base could be considered my 16, but my height, I don't think I have a height labeled here. A slanted height is not appropriate height. Height has to be perpendicular to the base. So it has to be going straight up from the side or straight down here in the center. So the height that we're going to be interested in is here right down the center. And I put a little box on the edge to show that that, to be height, would have to be perpendicular to that base. Now I don't know what that value is, but if I zoom in and look at just that triangle, then I could have a right triangle and maybe use the Pythagorean theorem. But as I look at it, 16 goes all the way across. I just need to know what this little part is. So I need to think more about what is this dotted line. Let's consider this point. And remember a theorem that you've learned in the past. If a point is equidistant to the endpoint of a segment, let's take a look. That point is equidistant to the segment that's 16. It takes 17 to get out to there, it takes 17 to get out to that part, and it's equidistant to the endpoints of that third side. Then it's on the perpendicular bisector. So if you're on the perpendicular bisector, we now know that both of these parts are 8. We could have assumed that, we could have wished it was true, but now we know that it's true. Now since we know that this is the perpendicular bisector, we can use the Pythagorean theorem to help us calculate the height. So we're going to use this triangle, which is 8. Our unknown, let's call it h for height. Not hypotenuse, but height. And the hypotenuse would be 17. It's across from the right angle. So hypotenuse squared, 17 squared, equals h squared plus 8 squared. 17 squared is going to be 289. Subtract the 64 across. Gives you 225. So when you take the square root of 225, h is going to be 15. Now if you look at this, that's that topic I talked about before. It's called the Pythagorean Triple. It's 3 numbers that are all whole numbers, positive integers. It's not a decimal, so the height is 15. Now since we know the height of the triangle, we can now find the area of the triangle. Area equals half the base, which is 16, and the height, which is 15. Half 240 gives us 120, and these units are in meters, so it's meters squared. So that's a pretty involved question. Be sure you understand some of the details about it. Here we have an isosceles triangle. It's equal distance down to the endpoints. So we know that the point where the two congruent sides touch is on the perpendicular bisector. So we know that it cuts this base side exactly in half. So we can use that in our advantage to do the Pythagorean Theorem. And that helps us find the height of the triangle, because 17 is not perpendicular. The height has to be perpendicular. So that gets us the value of 15, which helps us calculate the area of the whole triangle. So we use the whole 16. I've mentioned this a few times now, but the Pythagorean Triple is a set of 3 positive integers that satisfy the equation c squared equals a squared plus b squared. That's also known as hypotenuse squared equals leg squared plus leg squared. Now when we look at these numbers, the ones that are in bold are the ones that you need to be most familiar with. The ones that aren't in bold, underneath it, are multiples of the ones that are in bold. Let's see what a Pythagorean triple means. If it follows this pattern, then the leg squared and leg squared has to equal the hypotenuse squared. 9 plus 16 equals 25. That's true. 25 and 144 adds together to be 169. That's true. 64 and 225 adds up to be 289. And that works. 49 and 576 add together to be 625. Again, those are all Pythagorean triples. The two that are going to be most common that you're going to see on the ACT or SAT, even on the PSAT, will be definitely these two, but those other two do occur. And the main advantage of the Pythagorean triple is that it helps you get through the problem faster. You don't have to take time writing out an equation to solve for it. If you see the pattern, like we could have here, if you would have seen the 8 and the 17, maybe you would have noticed that, well, that's following a pattern. It's a right triangle. The hypotenuse is 17. One of the legs is 8. I know the other leg has to be. The only option possible is to be 15. It couldn't be 14 if it wanted to. It couldn't be longer if it wished it was. These other numbers are multiples. The 6, 8, and 10 is a multiple of 2, or multiples of 3 to get down to 9, 12, and 15. 16, 30, 34 are multiples of 2, or multiples of 3 to get down to the middle, or even multiples of 10. There's an infinite number of Pythagorean triples. The ones you need to be most familiar with are the ones in bold. On the next side, we're looking at this box, and the box is really the bottom of the other side, that the 3x, 4x, and 5x are the ratios that we're multiplying this common number to find out other Pythagorean triples. The 5, 12, 13, 8, 15, 17, and also the 7, 24, 25. Those are the common ones you need to be aware of. So when we look at this problem, we see that we have a 30, a 40, and we just don't know what that other side is. Well, if you would lay out a 30, maybe 30 inches or 30 centimeters, 30 feet, and 40 going the other direction, there's only one exact value that's going to match it here in the center. And it can be calculated using the Pythagorean Theorem, and it might be calculatable if we use Pythagorean Triple. It might work. It's not that all triangles make Pythagorean triples. We've had several that don't give us those whole numbers. So let's see what happens here. We know we have two legs. We have the 30 and we have the 40. We don't have this hypotenuse. That's our x. So what you need to ask yourself is what number goes into the 30 and the 40? So I recognize that 10 can go into both of those values. When I do that, it reduces down to 3, 4, and some other number. What is that other number? It's a pattern, 3, 4 something. It's a Pythagorean triple, I'm hoping. And if you look up, 3, 4, 5 is your Pythagorean triple. You would have to memorize that and know that it would be a 5 because it's following that pattern. Now the big question is, what do we do with the 5? X isn't 5. Remember, the hypotenuse has to be the longest side. But since we divided the 30 and the 40 by 10, we're going to take this 5 and multiply it by 10. So I know this missing side has to be 50. You could use Pythagorean Theorem just the same way as usual, and you would have gotten the same answer. But if you notice, this takes a lot less work, but it takes more understanding. Let's try this one. Here's the legs. We're looking for one of the legs. We don't know that leg. We know the 48 and we know the 50. So I'm going to ask myself, what number goes into both of those? Well, 2 goes into both of those. So some number, 24, 25, might be a Pythagorean triple. So when I start to come up looking at my list, 3, 4, 5, that didn't work. 5, 12, 13, 8, 15, 17, 7, 24, 25. So this number has to be a 7. So that's going to be the 7 to finish off the pattern. So now what do we do with this 7? Since we divided the other numbers by 2, we have to multiply to get to the 48. To get to the 50, we have to multiply by 2. So 7 times 2 gives you 14. So x is going to be 14. And that solves the right triangle for the missing side, and we used the Pythagorean triple as a method to do that. Remember, Pythagorean theorem would always work as long as you know two sides and you're looking for the third.